Hi all. In this video, we see a paper titled Monte-Carlo Research as a model predict controller for accomplishing lane following in autonomous driving. And this paper is unfortunately, from unknown authors. And this paper proposes an MCTS algorithms for taking continuous actions like steering, pedaling, and braking for accomplishing autonomous driving. And they compared this MCTS algorithm with the standardized MPC algorithm on a Udacity simulator in a lane following scenarios. So, in the introductions, the paper claims that autonomous driving is very important to make the car safer. And the reason is for every year there are many road crashes are happening all around the world, and it's costing around 518 billion globally. So this autonomous driving can be accomplished by three approaches. One is the classical approaches that we know that they have some many in the independent systems which are integrated together to build a world model like perception localizations, which rely on sensors or helps to build some kind of a world representations, and that representation is given to the some basic level low level controller, and the low level controller takes appropriate actions like steering and pedaling. So this is what the standardized approach, and it's been utilized in many very standardized systems like Google, Uber, and Baidu. The second system is like a video based, like end-to-end learning, where they have some few demonstrations, and from that demonstrations, especially from the human driving, they may directly input or map the video frames with the low level controller in order to compute the steering and pedaling. So mostly it's like a vision based regressor. The third approach would be like in between these two, and similarly, they use some images instead of directly computing the steering value. They try to compute certain affordances based on the traffic, and those affordances are like kind of a behavior layer, like in a standardized approach. That behavior layer helps us to identify which scenario the presently that autonomous driving is driving through, and based on that scenario the low level controller is being guided to in order to compute the steering and the pedaling. So there have been many attempts also been taken to bring the reinforcement learning into autonomous driving. And one among the thing is from that Mobileye proposed an architecture, which is again a two layer. Our upper layer is a high level path planning based on the recurrent neural network. And lower level is a model based reinforcement learning to accomplish the autonomous driving. And there are many other attempts that few things have been mentioned in this paper, like Hafeld has used human driver based reward functions, accommodation process been taken from the Bestar, and they have been using it to make dynamic Bayesian networks. The main proposed some asynchronous reinforcement learning framework to achieve a near human driving capability, and they claim that they could do this human level capability only within 12 hours of training this uh, and asynchronous reinforcement learning. So, but in this paper they have utilized, as mentioned earlier, a Monte-Carlo research algorithm which really helps to search in a very large exponential search space, and this has given a very promising results, especially in Go games. And the name, one of the famous name is like AlphaGo against the world leader called Mr. Lee Sedol. So on this MCTS algorithm is mainly applied for taking discrete actions, as we know in a board games like chess or Go, but it hasn't been never applied to the continuous. But there are few attempts. But we know that in autonomous driving, the actions are continuous. The one of the aim of this paper is to drive the autonomous vehicle within a track boundary, making this algorithm to be suitable to compute the braking, throttle, and the steering. So the aim of this objective is to proportion extension of the pure MCTS, which is especially applied for MCTS, to continuous actions. And moreover, it also compare it with the standard model predictive controller, which is being utilized for the low level um, controller, which is a model based. So there will be a model based MCTS and a model based MPC that will be compared, and we will see what results are given compared to these two algorithms. So other on as in background, there is two level hierarchical planning. One is a high level path planning, and that path planning information will be used like the vehicle controller like MPC or MCTS. And other approaches like RRT has been utilized, which also develop a feasible trajectory. From that, a best trajectory is chosen, and this is being asked for high degrees of freedom like differential drive. And MPC is usually for a short horizon problem, which is try to keep lane keeping scenarios. So the model is a simplistic linear model, a kinematic model, and it is like considered to be a two tires, and the state these are the state equations, and these are the state variable x, y, psi, and v. And x is something like x and y are the position, and this is the orientation, and this is the velocity, linear velocity. And this been represented as a simple linear equation like sk1 plus sk is the current state and sk1 is the future state, and E is the actions given that. And both the MPC and MCTS utilize this model to based on the other informations would be the high level, the trajectory what it has to be tracked, and also the deviation, lateral deviation is measured at the delta, and also omega is the deviation with respect to the heading angle. So based on these informations, we develop a cost function that has to be minimized both from the model predictor and MCTS, and this will be like kind of a time historic throttle time historic data from the delta and the omega. And also the theory also has to be smooth as much as possible. Based on this decided based on this how the weighting factors are put into these cost functions. So this MPC, we know that it uses this equations 2 as a cost function, and the model equation 1 as a modeling, and tries to make a model based optimization like optimal control, but for a limited number of steps like n steps truncated. And the first action is usually taken and given to the controller for the actuation, and the next the cycles repeats where, and the initial state will be considered as a present state. The same thing, the Monte-Carlo research that we try to explore. We have a enormous big space, so we tries to randomly build a tree, and that randomly build tree is iteratively updated to give a best actions. And this material is a pure MCTS, which is applied for discrete action as mentioned earlier. And it's a variant of MCTS is an upper confidence mode developed in 2006, and this is being utilized here. And one thing is it is tailored for here now as a continuous action. How it is being tailored is there are also have been attempted to build an MCTS purely for continuous action, but here the paper is trying to utilize the UCT, which is especially for the discrete action for this continuous action driving for steering and pedaling. Here they tries to say similar like UCT, they take go to the depth and expand the node. But one thing is the expansion is similar to like our building a path uh, instead of building over a different tree branches. And they have directly applying the continuing instead of using a discrete action, discretizing those steering and the pedaling values. So the algorithm is neatly explained in the figure one, like this called algorithm one. The input will be the system, the model what you have chosen is equation one and equation two, and decided number of steps would be like 8 steps in this in this paper. And the output would be that what it builds, that after the training it builds a policy which will give you the best actions for the minimize cost functions. The current state will be taken as the initial state, and the current actions will be taken as the initial actions. And for 8 time steps, it will be having for n number of sample parts. It generates the sample parts and tries to assign a cost function for every path. And from that all this one with the minimum lower cost will be the best path will be chosen, and that from that best path the first action will be taken as the best action, and it will be input to the actuator for the actuating, and the next updated will be repeated until we reach the desired goal or for the particular time steps. So they conducted this algorithm against MPC, in a Udacity simulator, and these are the weight factors that been utilized in equation 2. And for both the MPC and MCD, n is something like 8 steps, and the target speed is around 70 kilometers. And these are the results they obtained here, and we could able to see that the cost functions of MCT is much lower compared to the MPC of different time steps. And also MCT has tried to maintain as much high speed as compared to the MPC, which we are not able to achieve it. And another one important key factor the author tried to claim here is that MCTS could able to logically predict when to lower the speed and when to increase the speed. And especially they say that they can adapt to the speed during the curvature in the track. And those sampling paths are being utilized using the it is centered around the present time zone and making a uniform distributions to take the sample randomly sampling the paths. But author also says that it's not necessary to be uniform sampling, it can also be adapted based on the training. So this paper have given some kind of idea how to utilize MCTS for doing a lane following in autonomous driving, for directly computing the action steering instead of discretizing in a action space. And they compared with the standardized model predictive control, which is being utilized in nowadays for autonomous driving, which is standardized model predictive standardized model based controller. And with the comparative study, they says that the MCTS can make a better adaptation in the speed and the steering based on the nature of the track curvatures. And the future attempt would be to make more explorations of how to improvise this reinforcement learning and MCTS for further utilizing for the realistic autonomous driving. Thank you.